All right, guys, this is Mr. S here going through some notes on the kinetic molecular theory of gases. We often shorten the kinetic molecular theory to just be written as KMT. You'll often see this referenced on the calendar and in upcoming packet pages. It's just a shorter way of representing this big idea. The first thing that you'll notice at the top of this notes page is that there are several assumptions that we have to make about gases in order to apply the kinetic molecular theory, which is going to be a way of looking at the relationship between the variables that we can look at in each gas sample. Now, for all of our purposes, these five assumptions will always be true. As you get to more college level chemistry or more complicated chemistry, that's when you'll start to look at exceptions to these. But for our purposes, these five assumptions will always take place. Now, the main body of the notes here on this first page are the seven variables that we're going to use to describe something in the model of the kinetic molecular theory. Whenever you solve every kinetic molecular theory problem, you'll always have to include these seven variables. The first variable is moles, so the number of moles of the gas particle. That literally means how many particles are inside of the container, the number of particles. The second thing we want to always mention is the container type. So there are three different types of possible containers. The first one is if it's a closed container, and then there's two different distinctions that we make. It can either be closed flexible, which means that the volume can change. So the example given is like a balloon. So the volume of a balloon can get bigger or smaller depending on what other things you change about it. But the particles inside the balloon are still trapped, right? Once you tie the knot on the balloon, you can't add any more gas particles to the inside. The second option is what happens if you have a closed inflexible container. So an example is like an aerosol can, which is like a spray paint can or hairspray, where that metal can can't change its shape. It's fixed in whatever metal shape it was pressed into. Again, air particles are trapped inside. The third option is what happens if it's an open container. So that means there's an opening in the top. Imagine like a pop can that you've already cracked the lid to. Gas can go in through that opening, it could come out through the opening. The number of particles can change in the sample. The next variable is volume, which just represents the amount of space that the gas takes up. The collisions, which we represent with a C, so that's the gas particles bouncing into the sides of the container. A measure of the amount of collisions that is occurring is what we call pressure. So collisions and pressure are going to be closely related. Kinetic energy, this is the amount of energy due to motion of those particles. And then the average kinetic energy for a sample, that's what we defined as temperature. So temperature is a measure of the average kinetic energy. So again, kinetic energy and temperature are going to be closely related. Some of the variables have predictable relationships, which are listed at the bottom. So the first one is temperature and kinetic energy have a direct relationship. So if we think about increasing the temperature of a sample, that means that the kinetic energy will also increase. If you decrease one of them, then the other one will also decrease. They're always going to be going in the same direction. The same thing will be true of collisions and pressure if it's a closed inflexible container. So if we start talking about open containers, then things start to change because gas particles can enter or escape. So it has to be closed and inflexible. But in this case, if collisions goes up, pressure will also go up. If pressure goes, or excuse me, if collisions goes down, then pressure would also go down. They're always going to go in the same direction. Another one that's similar to this is collisions and volume, but now we're talking about a closed flexible container. So if you have something like a balloon, the balloon shape will change depending on how many collisions are occurring because the pressure inside of the balloon always wants to match the pressure that's outside of the balloon. So the balloon will increase in volume so that those pressures maintain the same, or it can decrease in volume. Notice there's a question here that says, will it go up indefinitely? Some of the harder questions that we look at, we'll look at, well, eventually you can only inflate a balloon so much and it's going to pop. Your car tires can only inflate so much before they pop. So there will be exceptions to this. If you flip over to the top of the next page, this gets at the idea of some of the basic relationships that we can look at. So it says, as the temperature of a gas in a closed, inflexible container increases, will the particles speed up, slow down, or have no change? Remember we said in a closed, inflexible container, temperature and kinetic energy are directly related. And if they're directly related, then whatever one of them does, the other will also follow. So if the sample of gas increases in temperature, then the particles will speed up. Direct relationship. And it says which of the seven variables refers to the speed of the gas particles. So that's the kinetic energy, the energy due to the motion of the particles. Question 2 says, as the volume of a closed container containing a sample of gas becomes smaller, will the collisions of the gas particles inside the container increase, decrease, or stay the same? As you squeeze those gas particles into a smaller and smaller space, the collisions are going to naturally go up because there's not as much room for those particles to move around. as you squeeze them closer and closer, if the collisions are going up, then that also means that the pressure goes up because collisions and pressure are going to have a direct relationship. So what will happen to the pressure? It will also increase as the collisions increase. Alrighty, number 3 says a balloon inflated to a diameter of 10 inches is inflated to a diameter of 10 inches and closed off. Atmospheric gases, the air, are colliding with the balloon on the outside while the gas sample in the balloon is colliding with the interior of the balloon. Does the inside of the balloon have a pressure less than, greater than, or equal to the atmospheric pressure? So we have to remember that a balloon is a flexible container, and a flexible container will always change its shape, either increasing or decreasing, so that the pressure inside the balloon is equal to the pressure outside. If the pressures were unequal, then the balloon would just shrink in size or get bigger in size in order to get those pressures to be equal. So the pressure inside will always be equal to the pressure outside the balloon. All right. Number 4 says a sample of gas is trapped in a solid container with a movable piston. Is the container flexible or inflexible? This becomes a little bit more challenging. It's movable, but a piston is a metal device it's very difficult to move. So if you imagine you've got a cylinder here, and then we've got a metal cylinder slotted inside of it. This is how like your car engine works. You've got a space in here that's going to have a specific volume, and you can move this metal cylinder up and down and change that volume. However, it's really hard for a gas to do that on its own. So something like a piston, you can change the volume. So that would have to be something that was provided in the problem or given to you in the outset. So you can change the volume. But in terms of the actual gas that we're looking at inside of there, we're going to assume that it's inflexible for the gas unless you're specifically changing it. So you would squeeze it closer and then we'd check and see what happens. It won't force the piston back out. It would be too hard for the gas to do. Again, there are exceptions to this. Your internal combustion engine forces those pistons out all the time, but that's a little bit more complicated than we're getting at right now. If you flip over to the next page, we start getting into some actual explanations where we're looking at actual pictures. So in this first picture, it references the speed of the particles, at least this top little graph here. The arrow represents the speed. So the longer arrow you draw implies that the particles are moving faster in that sample. This first picture, notice that all of the arrows are the same size. So it implies that the temperature of the first spray paint can is exactly the same as the second spray paint can, but it says that you are adding more gas. If you're adding more gas, it says which of the 7 variables are you changing? Well, the amount of gas inside of that container is always what we refer to as the number of moles of the gas particle. So it's the N in that particular case. Now this one asks us a series of questions and then it asks for the KMT explanation. So let's actually go through and do this. So in the space provided, it says give the KMT's explanation. I always like to touch on the container type first because that often dictates how the other variables are going to interact. So if we're talking about a spray paint can, that's a closed container, unless it says we have our finger on the nozzle on the top and it's releasing gas, then we assume that it's closed. No gas can get in or out. And a spray paint can is made of metal, so it's an inflexible container. So it's a closed, inflexible container. Now then the first variable that I always like to write down is whichever one we're changing. So in this case, it says you are adding more gas. So we're increasing the number of moles. Instead of writing the words increase, I just like to use an upward arrow. Decrease would be a downward arrow. It just makes it a little bit easier to write. So we increase the number of moles. Now then we have to think about which variable is going to be impacted by the increase in the number of moles. Now, if we have more particles inside of that spray paint can, I can tell just from looking at the left picture versus the right picture, there's going to be more collisions just because there are more chances for those particles to bounce against the wall. So if there are more moles, then there's going to be more collisions between those new particles and the walls of the container. And then if we remember the relationship between collisions and pressure of a closed inflexible container, they have a direct relationship. So if collisions goes up, pressure is always going to be the next one that we talk about. So pressure goes up. Now then the final question here says, what is the same between the two pictures? So we have to think about what were the constants in this situation. Not every variable changes each time. For example, did we change the temperature of the aerosol can from the before to the after picture? No, we said the arrow stayed the same size, so temperature stays the same. And which variable is always directly connected to temperature? Well, that's kinetic energy. So kinetic energy didn't change either. The last variable that doesn't change has to do with the size of this aerosol can. We said it was closed and inflexible, so the can didn't get bigger or get smaller. So we would say that the volume remained constant as well. That gas still occupied the same amount of space. We just had more particles. All right, first one down. Flip over to the next page. Okay. Now this one gives us a picture of a small balloon and then a picture of a larger balloon. Remember that a balloon is a flexible container where the pressure inside is always equal to the pressure outside. That's how flexible containers will always work. And then we increase the temperature by putting a match under it. Now, if we were to draw little arrows, our first balloon has a lower temperature. So if I would draw smaller arrows. As the temperature of that balloon gets bigger, I would represent that by drawing longer arrows for the gas particles that are in this balloon. Maybe they're bouncing off the walls, they're flying around, but the arrow length gets bigger. So then we have to ask ourselves, how are things changing in this balloon? Let's talk about the container type first. So in this case, a balloon is closed, right? It has a knot tied on the bottom, but it's flexible. It can increase its volume or decrease its volume depending on what's going on. Now, the first variable is always the one that we are changing. So we are increasing the temperature of the air inside the balloon. We're heating it up, not so much that we actually melt a hole in the side of the balloon and pop it, but just getting that air a little bit warmer. If temperature changes, the variable that's always directly related to temperature is kinetic energy. So that will always be the next one that we write. So now we have to imagine the particles are flying around that balloon faster and faster. Their kinetic energy is increased. If they're flying around faster and faster, then they're going to start colliding with the walls more and more frequently. So the collisions goes up. Now, as the collisions go up inside of a flexible container, this is where things get a little tricky. We know that the volume of that container can go up until the pressure inside the balloon is equal to the pressure outside the balloon. So we always want to keep the pressures in versus outside the balloon constant. So as the collisions start going up, notice that the volume of the balloon gets a little bit bigger. The volume compensates for the greater activity of the particles inside. So when we think about our constants for this situation, well, we didn't add any more particles or take any gas particles away, so moles is going to be a constant. We said volume changed, we said temperature changed, and kinetic energy changed. So then the only things that we really have to think about, and technically we said that the collisions went up and that the pressure remained constant. So really we'd think that collisions and pressure remain constant. We know that they did go up a little bit, and that's why the volume of the balloon had to get bigger. So that's a little bit tricky. You may want to ask your teacher how to specifically go about that. As long as you include your explanation or at least some explanation of why the variables are doing what they're doing, I will typically mark that as correct. Won't get too nitpicky on you. So that sums it up. Practice the next couple of pages. There's a few examples that all look at the same type of thing, and then check your answers using the online answer keys once you're done.